Let's spend some time to learn how to count in different bases. We will see that counting follows the same pattern in every base, but the point at which we move to the next position changes. The number system we use most often is called base 10. This is also called the decimal system. It uses 10 symbols: 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. These are the digits we normally use every day. In base 10, once we used all 10 symbols, we move to the next position. So we count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we write 1, 0. But here, 1, 0 should not be thought of as just the word 10. It means one group of 10 and 0 extra ones. That is the idea behind counting in any base. A base tells us how many symbols we can use before we move to the next position. In base 10, we have 10 symbols. In base 4, we have 4 symbols. In base 2, we have 2 symbols. In base 8, we have 8 symbols. In base 16, we have 16 symbols. Let's look at base 4 first. In base 4, the available symbols are 0, 1, 2, and 3. So we count 0, 1, 2, 3. After 3, there is no next single digit. So we move to the next position and write 1, 0. In base 4, 1, 0 means one group of 4 and 0 extra ones. Then we continue 1, 1, 1, 2, 1, 3. These mean one group of 4 with 1, 2, or 3 extra ones. After 1, 3, the rightmost position has again gone through all of the available symbols. So we increase the position on the left. We get 2, 0. In base 4, 2, 0 means two groups of 4 and 0 extra ones. Then we continue 2, 1, 2, 2, 2, 3. After that comes 3, 0, 3, 1, 3, 2, 3, 3. After 3, 3, both positions have reached the largest available symbol. So we need a new position. We write 1, 0, 0. In base 4, 1, 0, 0 means one group of 16s, 0 groups of 4, and 0 extra ones. This happens because the positions in base 4 are powers of 4. The rightmost position is 4 to the power of 0. Since 4 to the power of 0 is equals to 1, it counts ones. The next position is 4 to the power of 1. Since 4 to the power of 1 is equal to 4, it counts groups of 4. The next position is 4 to the power of 2. Since 4 to the power of 2 is equal to 16, it counts groups of 16. This is the same idea we use in base 10. In base 10, the positions are powers of 10. The rightmost position is 10 to the power of 0, which counts ones. The next position is 10 to the power of 1, which counts tens. The next position is 10 to the power of 2, which counts hundreds. For example, the number 425 means 4 hundreds, 2 tens, and 5 ones. So we can write it as 4 times 10 to the power of 2 plus 2 times 10 to the power of 1 plus 5 times 10 to the power of 0. Here, 10 is the base. The exponents tell us the positions, starting from 0 on the right-hand side. Now let's look at binary. Binary is base 2. It uses only two symbols, 0 and 1. So we count 0, 1. After 1, there is no next single digit. So we move to the next position and write 1, 0. In binary, 1, 0 means one group of 2 and 0 extra ones. Then we continue 1, 1. This means one group of 2 and 1 extra 1. After 1, 1, both positions have reached the largest available symbol. So we need a new position and write 1, 0, 0. In binary, 1, 0, 0 means one group of 4, 0 groups of 2, and 0 extra ones. So the binary counting pattern starts as 0, 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 1, 0, 0, 0. This may look strange at first, because 1, 0 looks like 10 to us. But in binary, 1, 0 is not 10. It is one group of 2. The symbols are the same as decimal symbols, but the base changes what the positions mean. Now let's look at base 8. Base 8 is also called octal. It uses 8 symbols: 0, 1, 2, 3, 4, 5, 6, and 7. So we count 0, 1, 2, 3, 4, 5, 6, 7. After 7, we move to the next position and write 1, 0. In base 8, 1, 0 means one group of 8 and 0 extra ones. Then we continue 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7. After 1, 7, we move to 2, 0. This means two groups of 8 and 0 extra ones. Now let's look at base 16. Base 16 is called hexadecimal. It needs 16 symbols. We usually write them as 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. The letters are used because we need symbols for values beyond 9. So A represents the next single symbol after 9. Then B, C, D, E, and F follow. In hexadecimal, we count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. After F, there is no next single symbol, so we write 1, 0. In hexadecimal, 1, 0 means one group of 16 and 0 extra ones. This shows why we need to be careful when reading numbers in different bases. The representation 1, 0 does not always mean the same quantity. In base 2, 1, 0 means 2. In base 4, 1, 0 means 4. In base 8, 1, 0 means 8. In base 10, 1, 0 means 10. In base 16, 1, 0 means 16. The written symbols can look the same, but the base tells us what quantity is actually being represented. This is why we often write the base as a small subscript. For example, 1, 0 with a small 2 at the bottom. which means 1 0 in base 2, or 1 0 with a small 8, which means 1 0 in base 8, or 1 0 with a small 16 at the bottom, which means 1 0 in base 16. The subscript tells us how to interpret the symbols. The intuition behind counting in different bases is that every base is just a different grouping system. Base 10 groups things in 10s, base 2 groups things in 2s, base 8 groups things in 8s, and base 16 groups things in 16s. Counting moves from right to left. The rightmost position counts individual ones. When that position runs out of symbols, we form one group off the base and move it to the next position. When the next position runs out, we form a larger group and move again. So a number is not just a string of symbols anymore. It is a record of how many groups of each size we have.